Okay, 13.3. Kepler's laws. There's 3 laws of Kepler, like 3 laws of Newton. There's Kepler's laws of planetary motion. He was a disciple or pupil of Tycho Brahe. And 16 years of looking over astronomical data, he concluded that all planets move in elliptical orbits. And these different orbits, they have something called eccentricity. So some of them are more elliptical than others, or more, quotes, eccentric than others. I think the Earth, if you will, is probably the least eccentric in its orbit. It has the least amount of elliptical shape, but eccentricity is level at E. And then if you go into higher levels of physics, you're going to see, you know, the differences. E equals 1, I believe, is for a perfect circle. And then the higher numbers, all the way up, you know, 7 or whatever it is, you know, you get different types of elliptical orbits or even hyperbolic orbits, like comets coming in with hyperbola. So there are different levels of eccentricity, but all planets move in elliptical orbits. Secondly, this one's a little bit cumbersome. And let's go to a question. Yeah, I got it. Yeah, thanks for that correction. Yeah, because I forget that sometimes. 1 or 0 baseline, you know, like, you know, zeros and ones. Yeah, and again, I won't belabor the detail of that because we get, you know, down in the weeds, but there's different eccentricities for the orbits. Radius vector drawn from the sun to planet sweeps out equal areas in equal times. So basically, you have an ellipse, you have the sun, you have the Earth here. This area here, you know, between, let's say it goes to here and here, so there's TI, T final. This area here is going to be swept out in the same amount of time as, say, this area here. Like if when the Earth is here, you know, and then it continues to revolve around the sun, orbit around the sun. These 2 areas are going to be the same in the same amount of time. That's all that's saying. Radius vector drawn from sun to planet sweeps out equal areas in equal times. The time difference here is the same as the time difference there. And it's the ellipse, and there's one of the foci of the ellipse. These are 2 foci, foci, and the sun being here is at one of the foci, and the Earth is doing its orbit in an ellipse, or Mars, or whatever. So that's what the second law is all about. Equal areas, equal times. So that this is, say, A1, and this is A2. Again, just putting that on the table and moving forward. 3, the orbital period, or the square of the orbital period, or the time it takes to go around the sun once, let's say, is proportional to the radius cubed. So basically, the orbital period squared is proportional to radius cubed. So squared is proportional to the radius vector cubed. We can prove that real quick. So let's go to the third law. Oh, sorry if I didn't leave that up another 30 seconds or something. All right. So in the third law situation, so let's say we have the sun here. I want to make it kind of basically a circle. Eccentricity is 0. Let's say we have the Earth here, and it has a tangential velocity going around in a circle like so. We have this situation in the Sun Earth system. We know that the reason why the orbit is there because of the force of gravity, the universal force of gravity between the sun with respect to the Earth keeps it revolving around. So we have this invisible string of gravity that's tugging on the Earth as it whirls it around the sun, so to speak. And so we have, we've seen this equation already, universal force of gravity, where mass of the sun, mass of Earth over radius squared is going to be equal to the centripetal force. That is the force that's making up the net force, which is a centripetal force. And mass of Earth in question, that's the mass being acted on with respect to the sun, and vice versa if it's the Earth. So mass times acceleration, where we know acceleration is equal to mv squared over r, right? Or the centripetal acceleration. Centripetal force is the force of gravity. So then we can just kind of like start knocking this down. All we're trying to do is trying to get a relationship between that force and the orbits. Sun Earth system, I just said we have, yeah. And then let me just slow down just a bit. Don't want to, yeah. So again, the universal force of gravity, the two masses in question, the Earth and Sun, and the radial distance between the two from their centers of mass, which we'll be talking about on Monday, and mass of Earth, centripetal acceleration, MEV squared over R. Then we have, cancel out the MEs. Right, like so. And so we have, okay, so all we're trying to do now, I mean, obviously before, we come up with Kepler's third law, we're just trying to get a relationship between the orbital period and the radius. Why? We're curious. How much time can we get a relationship between the distance between the Earth and the sun, or some other planet and the sun, or two masses, period? Is there a relationship between, that distance and the time it takes to go around? Okay, we know there is intrinsically because we have velocity in there, because, velocity is going to be the circumference over period, distance over time. And so we know there's a relationship, but we're just trying to see what it is, what exactly that relationship is. So we know that velocity is 2 pi r over t. T is the orbital period, and this is the circumference or distance around the circle, right? Distance over time. So we can substitute that into our equation that we have now, and let's get that relationship between the two. And so we have G mass of sun over r squared, keeping the t squared over radius, because it's velocity squared over r, velocity squared over r. equals 4 pi squared r squared over t squared over r. So that r cancels out there. We left with this guy up top, and I'm just going to keep that in line here. I don't want 1 over t. I want to get just t. So I'm going to flip everything, and I have r squared over g mass of sun, because remember this numerator becomes a denominator. You're going to have t squared over 4 pi squared r. And so now when I multiply both sides by r over here, I'm going to get r cubed, t squared. We got that relationship. Not that it equals, it's proportional to. Right? So that's Kepler's third law. That the square of the orbital period, square of the orbital period is proportional to the radius vector cubed. Okay, so there we go. Third law. So we can use that in certain problems. So then, if I wanted to just do this in terms of t squared is equal to 4 pi squared r cubed over GMS, or just whatever the largest mass, or in this case, mass of the sun. So this number here, this is a constant because we know the mass of sun is going to always be the sun, and then G is a constant pi. So this is known as like the Kepler constant, Kepler number. So we have this t squared equals k r cubed, if you will. So again, we have the proportionality between t squared and r cubed there for the third law. I'm going to skip over section 4 because section 4, all it's talking about is that the gravitational field strength at the Earth is given by G, 9.81. So they're just expanding on the idea of what it means by gravitational field. So it's kind of like a we already know kind of thing. So nothing, and the reason why I do that is because there's nothing really new about that section in context. Gravitational field strength is really the gravity at that particular surface. For Earth, 9.8. Mars, 3.7. Moon, 1.6. Jupiter, 25 times Earth, or we can get whatever that number is, right? So like for the Earth, we know magnitude, 9.81 meters per second squared, direction negative 9.81 meters per second squared. Okay, 13.5 and 6. Are next. So I like to call this universal potential energy. Potential energy is really just the integral of force. I'm not going to integrate it. Okay, cumbersome, and I don't know who's not in calculus here. I'm not going to waste your time. I'm just going to give it to you. All right. We know that kinetic energy, period. At least let's think about that planet. Let's think about Earth going around the sun. Kinetic energy 1/2 mv squared. VT, the tangential velocity, 1/2 mvt squared if you want to denote that that's a tangential velocity. And potential energy, or the so-called universal potential energy, given which is the integral of of Newton's law of gravitation, is going to be just this guy right here, G M, or I just say in terms of the arbitrary masses, M1, M2 over R. So this is what is the universal potential, or the potential energy between any two masses, not just you and the Earth, asteroid and comet, you know? And so that would be the energy of the system. So it's the potential to do work. And always think about it in terms of that. You have an atom, electron, nucleus. It has a potential energy given by this equation here. You know, at least in concept, but intrinsically that's the potential energy of that system, which is the same concept as Earth going around the sun. This is the potential energy of a two-body system: electron, proton, Earth, sun, given by this. You can calculate it. Also, not only is this potential energy, so okay, so you have any two masses, center of mass. This is a bound state. This is the energy of that system, Earth, sun, the potential to do some sort of work. The magnitude of this potential energy, the actual number, that's called the bound energy, or binding energy, sorry. It's basically the energy responsible for binding these two masses together, if you will. The energy of that system, because we know from first principles that potential energy is relative to some distance between two masses. I got a ball above the ground. I have a potential energy, mgh. This is the same concept. So G is the gravitational force between the two, and R is the space between them. G, big G, is the gravitational constant. It is this constant that relates to this universal gravity. So the universal gravitational force is this whole thing. G is this constant that, well, relates the left and right hand side. You know, kind of like x equals vt, displacement equals velocity times time. Velocity relates distance and time. Same function. So that's, I mean, just think about it. You're comfortable with this picture. You're comfortable with the basics of quantum mechanics, because when you get down to that level, you're looking at the bounding energy between the electron and proton. And this electron could be in higher states, in states of energy, or integral steps, discrete energy steps of this energy, where the discrete levels are given by n equals 1, 2, all, and so on and so forth. So if it's in energy state 2, doesn't mean it's in orbit 2. It means that the energy is in another state in that same orbit. So we can have so when it's at n equals 1, we call it the ground state. So this potential energy here between Earth and sun, let's say, is the ground state, or binding energy, or potential energy, all the same thing. And since on a large level, physically, this mass can't really be excited to some other energy state, unlike down there in quantum mechanics when we're dealing with waves, and waves can exist in different states. This energy here is going to this is always going to be constant. This is going to be the bound energy, the binding energy between this Earth and this sun. And Mars is going to have a different binding energy because of the distance. Any questions there? You got that? Because that is a key deal. Okay, so piggybacking or expanding on that idea is now we're going to take this orbit with this energy and that potential energy and that kinetic energy, put them together into what we call the total energy of the system. We know that by itself, this is the binding energy of the system, the potential energy between Earth and Sun. Now, we know that this is also rotating. Tangential velocity has kinetic as well, kinetic and potential at all times. When you add them together, first principles, what do you get? Anyone? When you add kinetic and potential, what do you get?
Mechanical?
I'm sorry?
Mechanical?
Yeah, the total mechanical energy. Yes, it's the total mechanical energy of the system, because by definition, our perspectives changed here. We're in an orbit, whether we have a bird flying with a fish, he's moving kinetic energy and he's above the ground. That's a total energy because he's got motion and he's got a height. Same thing here, motion and a height, R. So when we add them together, we get what is called the total energy of the, like you said, saying the total mechanical energy. Because now we're dealing with mechanics, velocity, acceleration, and stuff. So let's see what that. See what that looks like. Energy considerations. Planetary motion. So the Earth-Sun system, the total energy is kinetic and potential. Usually they give the symbol U because instead of writing PE all the time, U for potential energy. And so that's helpful too, because then I erroneously used to think that those end states of energy, oh, those are different orbits, but how can they be there? Of course they're not, because like hydrogen, for example, only has one freaking electron, so it can't be different orbits, different states of energy. Like, I have mv squared minus g, I'm going to say m, capital M for like, sun and earth over r. Now we're going to find out that the total energy in the system can be positive, negative, or zero. Okay, the total energy. This equation here is a total energy equation. Not conservation, it's just that energy is made up of kinetic and potential. Because we know that conservation deals with the changes. Yes, you are correct also. Nicole, total energy, mechanical energy. This total energy be positive, negative, or zero. Zero if you have no distance and it's not moving, but that's kind of not useful. And E, the energy can be less than zero. Due to U going to zero as R goes to infinity. So so this basically what this can be less than 0 under those conditions. If this radius, if you go all the way to infinite distance, the potential energy goes to nothing in the system. This basically that's the case. It can be less than 0. But let's see if we can derive, carry this through mathematically to see how it can be less than 0. That may be a foreign concept, like energy being less than zero. Like, how can we deal with that? So let's play with this case. Or better yet, let's take a look at the Earth-Sun system and play around with it and see what we find out about the energies. So consider the Sun-Earth system. Once again, big mass, we know there's much greater than the small mass. We know that the gravitational force is big M times M over R squared. And that's the centripetal force. It's equal to the centripetal force there. Okay. Please let me know if I'm going too fast. I don't want to. I think I'm going at a good pace, but please stop me. I'll try to monitor that. But does everybody have things up to this point? Anybody still writing? Because if we need to, we'll spend like the first part of next class going back over this. And maybe possibly we can do the gravitational lab in class. It's something different, just to kind of, we gotta mix, we gotta, mix that up and stuff. Okay, now let's take take this equation. And what I'm going to attempt to do is take the total energy equation up top, and in terms of what I have already, I want to get this kinetic energy term in something that looks like this, because I want to see, the point of this overarching point is to see if energy is less than 0, positive or negative, right? And I can't do that unless my terms are the same, and I can't add or subtract if I don't have the same terms. So in order to get that way, let's multiply both sides by R. And then I have this, I have G MM over R equals MV squared. So basically, I'm trying to get an expression of kinetic energy in terms of something that looks like the potential energy. Why? Because I want to add or subtract like terms. So it's MV squared. Okay, it's close. But if I get 1/2 MV squared, I got to divide both sides by 2. So I get G MM over 2R equals 1/2 MV squared. Okay, now I can sub this back into my original equation. Let's carry it through. Can energy be positive, negative, or what? And that's going to be the bound state energy, or let me get that, the total energy in that system. Because I made a misstatement there. It's not going to be bound state, but the total energy, because the bound state or the binding energy deals with the potential. The energy that exists without motion, like you have an atom or a nucleus of an atom, it's just still, relatively. The energy there is the binding energy. There's no rotations at all. In this case, there would be rotations as well as distance. Okay, so E is equal to G mm over 2R minus, see, I made the substitution right here. That was 1/2 mv squared. G mm over R. You do your like terms and your common denominators. See, right? Because I can't add or subtract anything unless I have the terms to be the same. If I tried it from the original equation, it wouldn't work. But when you do this, now it just becomes a matter of, okay, common denominator. You're going to get the energy to be this value, G m over 2R. So this is the total energy in a planetary system, like say between the Earth and the Sun. So the energy in fact is negative, the total energy. Because the conditions were it can be positive, negative, in this case negative, or zero. We know that it's negative for circular planetary orbits. Any questions on that anywhere? This is the total energy between the Earth and the Sun. And it's negative. It might be kind of awful to see, but you can kind of get some appreciation for that because the potential energy is negative. So it's if you were to see the calculus derivation of that, maybe that'd be more appreciation for that. We're just going to take it on face value for the moment. Obviously, I'm not going to show you the calc way of seeing that. But total energy is planetary circular orbits, maybe a little counterintuitive, but it is negative, yes. And this is for circular, but for like elliptical orbits, there's like what in an ellipse there, it doesn't have a radius in an ellipse. The ellipse has what is called a semi-major axis. It's like ellipse. This will be the semi-major axis. Semi-major. And this would be the semi-minor. So there's not a radius per se of an ellipse. It's a semi-major axis. Again, I'm not going to put all the foci. There's 2 foci here in the planet. I'm not going to deal with the geometry of it, but just going to tell you what, semi-major axis is the horizontal part. Kind of acts like or looks like a radius, but it's not really. Why? Because this shifts. This is not going to be the same distance from the center over here as it is here. This is bigger out here than this. That's why it's minor. This is major. Okay, so semi-major axis is denoted by letter A, and the semi-minor would be the letter B. So we're going to take the total. So for an elliptical orbit, we're going to take the total energy to be negative G m over 2A, where A takes the place of R. So this is for elliptical orbits. Okay, and that'll just that'll stop us for now. The last thing that we're going to do is just derive this equation for escape velocity. What is the speed necessary to leave the Earth's gravity? And we're going to do a sample question in one of these sections and then move forward. But that's basically the basics of this. Total energy for circular orbits is negative, as well as for elliptical orbits. And we'll clean that up on Monday. Any last questions? You guys can take off. Hopefully you guys got through it. I will see you on Monday. Yes, you may. I'll be right here. Okay, I'll see you guys later. If you don't have any questions, see you Monday.
Mr. Kelly, so only the difference was that the radius changed?
Yeah, because an ellipse doesn't have a quote radius. It it gets longer and shorter at certain points.
Okay, thanks.
Okay,
Have a good day.
okay. Later.
Hello, Mr. Kelly. So yeah, I do this every test. I'm sorry, but like
It's okay.
for the test today, I noticed like when I was solving it that I had like a little trouble getting past like the actual math part, like drawing the free body diagrams was fine. I got where the tension was, I got where the angles and the sines and the cosines were, but getting to the actual math and